Good afternoon, everyone. So people are still coming in, so I'm as well just getting started. I'm going to talk about transactional data structures, which is a step beyond non-blocking or concurrent data structures. I'm Delhi, and I recently graduated University of Central Florida and joined Microsoft. And most of the talk is based on research projects that's been done in UCF together with my advisor, Dr. Dechev. So in this talk, I'm going to first discuss what transactional data structures are and why we need them in concurrent programming. And I'll explain 3 pieces of methodologies that will enable us to build high-performance transactional data structures in C++. The multi-resource lock, lock-free transactional transformation, and the multi-dimensional list. Now, after that, I will show you some experimental results with the components and conclude the talk with a summary and discussion on future work. Now, as the beginning of the multi-core era, we know we have to exploit parallelism. And now we are already at the doorway of many-core era. Here is a picture of the Intel Xeon Phi processors with 72 full-fledged x86 cores. Now, this processor is due on the market in the following months. And in the same time, we have this year's #1 top 500 supercomputer goes to a new system built in China, which has 260 RISC cores. The many core chips are here. Do we have adequate software to take advantage of them? For the past 2 decades, researchers have been proposing a large number of non-blocking data structures. So these data structures, besides the great scalability, the most appealing aspect of them is that they support strong progress guarantees, such as weight freedom, lock freedom, and obstruction freedom. Weight freedom requires that all threads in the system must make progress in finite number of steps so that no one will starve. And the weaker lock freedom requires that at least one thread is making progress, so the whole system will not starve. And the obstruction freedom only requires a thread to make a progress without competing threads. We'll be focusing on lock freedom because it provides just enough progress guarantee without the overhead of weight-free synchronization. Now, the non-blocking data structures, they have a new set of correctness properties. Linearizability is the most widely adopted one. Linearizability is compositional, meaning that we can put multiple linearizable objects into a container library so that the library as a whole is still linearizable. As a result, we already have many of these libraries available on the internet, such as libcds, Turbo, and Intel's thread building blocks. Here is the graph showing the linearizable operations. We have 2 threads accessing 2 linearizable objects, A and B. So by identifying the linearization point indicated by the arrows, we could obtain a valid sequential history at the bottom so that the whole system is still linearizable. Now, all looks good, and it seems we have been doing a lot of work with this non-blocking data structure, so can we stop researching and put them to work? Unfortunately, all existing concurrent data structures, they miss a very important functionality, which is allow users to compose multiple operations together correctly. This is something we do effortlessly all the time with conventional sequential data structures. So here is a very simple example of a move function that tries to delete a key from set A and insert it into set B. In sequential scenario, this code would be trivially correct, but in concurrent execution, the operation might get interrupted right after deleting the key from set A, thus leaving the 2 sets in an inconsistent state. Now, what if we only have 1 container? That's not going to help. We still need additional synchronization. In the second example, we try to compute some value and put the new key value pair into the map only if the map does not already contain the key. The thread might get interrupted after the condition check, so the operation might wrongly overwrite an existing value in the map. A more complicated example involves 2 hash tables. Consider the program tries to maintain a forward map from a contact name to phone number and the reverse map from the phone number to names. If you want to update a phone number, then what you do is you update entry in the contact map and you delete old entry from the phone map and insert a new entry. All this have to happen in 1 atomic steps, but all concurrent data structures, they don't readily support this kind of transaction. The problem is that linearizable operations are still not composable, and many programs are not aware of this issue. So given the above example, if the two hash tables were using logs, then maybe the user can get it to work by acquiring all logs at the same time. But this requires the maps to expose the internal logs to the user, which breaks encapsulation. Or if the maps are constructed in a log-free manner, then there is nothing much user can do besides ask the library author to provide a new method that's manual composition, which leads to state explosion. So in order to support reusable software design in a modular fashion, we need to have transactional execution support in concurrent data structures. Now, similar to a database transaction, we say a data structure supports transactional execution if it can execute a sequence of operations atomically and in isolation. Atomicity requires that if one operation fails, the entire transaction should abort. And isolation requires that the concurrent execution of transaction appears to take effect in some sequential order that respect the real-time ordering. Now, if the data structure satisfies these two properties, we say it is strictly serializable. This is analog of linearizability for transactions. Now, let's review some of the current applicable approaches that we can use to build some preliminary transactional data structures. Given a sequential data structure, we can, of course, easily apply software transactional memory. Any code that's been wrapped between the TM begin and TM end will be executed in an atomic fashion. So here I show a simple example of insert function taken from a sequential order list. What we need to do is to notify the STM when we read and write a shared memory location by using the TM read and the TM write macro. We also need to let the STM take over the memory management. So in principle, an STM instruments thread memory accesses, which records the location of thread read in the read set and the write in the write set. Conflicts are detected among the read-write sets among different threads. So in the presence of conflict, only one transaction is allowed to commit, and the others will be aborted and restarted. So because STM instruments low-level memory accesses, it has large runtime overhead. And this is one of the reasons that STM hasn't been so widely used yet. And a more important aspect is that the low-level memory access conflict, they do not necessarily correspond to data structure level semantic conflicts. So this way, STM causes way more aborts than it needs to. Here is an example. Consider we have a linked list, and thread 1 and thread 2 tries to insert key 4 and 1, respectively. Now, any good concurrent implementation of linked list should allow these two operations to proceed concurrently, because they actually write to disjoint memory locations. But in an STM, they do have read-write conflicts on node 0, so STM has to abort one of them. To address the semantic conflict issue, Herlihy and Koskinen, they proposed the transactional boosting, which is actually a very cool technique to obtain transactional data structure from a base linearizable data structure. In transactional boosting, all we need is a linearizable data structure to start with, and each operation will need to acquire an abstract log before actually executed operation. So the abstract logs, they are designed based on the knowledge of commutativity of the data structure operations, so that they ensure that non-commutative operations will never occur concurrently. And in case of a transaction fail, the transaction will invoke the inverses of already executed operations to restore the abstract state of a data structure. Now, here is the specification of a scalar data type. We can see that the insert and remove function, they are actually commute with each other as long as the key they access are different. So the abstract log of a scalar data type will be associated with each data key. And for example, if a thread tries to insert key 2 and 3 at the same time in a transaction, it needs to acquire actually 2 logs, one associated with key 2 and the other associated with the key 3. Now, the problem with transactional boosting is that although it provides significantly better performance than STM, the use of logs degrades the progress guarantee when it's applied to log-free data structures. And as this graph shows, when a transaction fails to acquire a log, it has to roll back already executed transaction. In this case, it needs to insert the node 9 back into the data structure, which causes additional overhead because this rollback process does not contribute to the overall throughput. So I'm going to introduce some of the research work we did in order to build better performing transactional data structure in C++. The first piece is a multi-resource lock, which is a centralized lock manager that allows you to acquire multiple locks at once. And this can work together with a transactional boosting technique for legacy lock-based data structure to convert them into lock-based transactional data structure. And the second piece is the lock-free transactional transformation. This is actually a methodology to obtain high-performance transactional data structure from lock-free based data structures. So after the transformation, the data structure will still be lock-free while supporting transactions. Now, the third piece is a multidimensional linked list, which is a brand new search data structure designed from ground up that is optimized for concurrency and transaction support. So lastly, we need to put all these pieces together so that we can have a framework to support cross-container transactions, and the user can compose transactions among multiple instances of data structures. Now, before diving into details, I'll briefly review some of the techniques that we use in the lock-free programming. So the compare and swap is an atomic primitive that only updates the memory location if the current value matches our expectation. And most lock-free programs are based on cache-based retry loops in which the operation continuously to try to update a memory location using cache and until it succeeds. Now, the descriptor object is a small memory structure that will store the execution context of an operation. In case the execution of the operation is delayed or interrupted, another thread can pick this up and continue the execution. A cooperative execution is a mechanism for a thread to help each other finish unfinished pending operations. So a typical log-free code will look like this. Operation starts with a new operation and creates a new descriptor for this current operation, and it reads the current node and see if there is any pending operation. If so, it will set out to help finish the pending operation, and finally, it will try to update the descriptor on current node using the cache. Now, remember that transactional boosting requires an operation to acquire an abstract lock before execution. So for multiple operations in a transaction, the transaction boosting technique requires the data structure to acquire multiple locks. So if we treat each data item as a resource, then in this case, we can actually reduce the transactional synchronization problem to resource relocation problem, which says that given pool of k resources that require exclusive access, each thread may request 1 to k resources, and the thread should remain blocked until all the resources are available. Now, this can also seen as a generalization of the famous Dining philosopher's problem. Generally, there are two strategies to approach this problem. We can use locking protocols and assign a lock to individual resources and acquire the locks one by one. So this locking protocol has long been adopted by the database concurrency control, such that we have the two-phase locking resource hierarchy. In two-phase locking, we are only allowed to acquire locks in one phase and release them in another. And the resource hierarchy, we assign a total order to all the locks, and all threads should acquire them in the same order. Now, the problem with these locking protocols is that, especially with two-phase locking, is that when running on the shared memory system, they are prone to conflict and retry if the memory contention level is high. So another strategy is to actually acquire multiple locks in a batch, hence batch locking. MRLock is such an example, but before explaining it in details, I will briefly show you the extended TATAS lock, which is a simplified version of MRLock. Now, in the extended TATAS lock, each thread will encode its resource request in a bit set. And each bit will represent one resource. So the conflict among resource requests are detected using bitwise AND operation between the value B and R. And if there is no conflict, the lock value is updated using the bitwise OR operation and the cache. So this way, the lock can handle requests in batch. But there are a few drawbacks. It provides no fairness guarantee. So all threads are contending for the same memory location. So whoever wins the cache wins the access to the request. And it causes heavy contention, that's the same reason, because it has only one memory location for you to contend. Most importantly, it only supports a limited number of resources, because on a 64-bit system, you can only cache 64 bits at the same time. Now, in the MRLock, we introduce a array-based lock-free FIFO queue to replace the actual memory location, so that each thread has now allocated a cell to write its resource request. This way, we can guarantee FIFO fairness among contenders, and it can support unbounded number of resources, and can handle contention better. So how does MRLock works? The graph on the left shows that a thread while in queue is resource request into the queue, and it now scans from the head of the queue for resource conflict with any outstanding resource request. For example, in cell 5, a thread is requesting to access the last resource. So when it scans from the head, it sees no conflicts. Now it's good to go. It gains access to that resource. But when another thread in queue is requested in cell 6, it sees conflicts with the outstanding request in cell number 3. So now it has to wait, either a spin or whatever. Then when the when the thread holding the lock on cell number 3 releases it by setting the bits to 0, the thread now will scan on cell number 4, because there is still one outstanding resource conflict. Now, the data structure of the MRLock, for each cell, we store a bit set request, as well as a sequence number, which will be used as a synchronization sentinel. And the MRLock data structure itself contains only atomic head and tail index values, as well as the fixed size buffer. Now, during the initialization, we allocate the buffer and store all the bits to ones, and set the value of all the sequence number to equal to their cell index. The acquire function contains two parts. The first part is a cast-based loop, where we try to use cast to increment the tail position by 1. And if we succeed at this, it means that we allocate a new cell for this request, and we can write the request value into the bit set and increment the sequence number to indicate the cell has been taken. Now, in the second part is a while-based spin loop. It spins from the head of the queue to detect any outstanding resource conflict until reach the position allocated to this thread. Now, once the lock acquire function returns, it returns to the user a spin position, which will serve as a lock handle to be used in the release function. So to release a lock, the user passes in the lock handle, and the cell, the bit set in that associated cell will be set to 0. And next, we need to do one thing. We need to clear from the head to advance the head index, but we only do this if the bit set in the head cell has been already cleared. And if so, we will reset the bits in the cell to ones, and we will increment the sequence number in the bit set in that cell to indicate the cell is free to be reused again. So here is how the sequence number changes throughout the life cycle of the ring buffer. Initially, we use the sequence number to do bounce checking, and initially they were set to the index of each cell. With each in queue, the sequence number increased by 1. So when the tail wraps around, it sees that the current tail index does not equal to the cell index. So the cell is taken. It won't wrongly overwrite any existing value. When the head advances and releases a cell, it will increase the sequence number by size -1, so that the cell index now equals to the tail index. This indicates the cell is ready for reuse again. The concurrent update of the ring buffer is safe because through the use of the sequence number, we guarantee that the head always precedes the tail, and the tail is always larger than head by at most n, where n is the size of the ring buffer. Now, the important thing is that we don't need to use atomic operations to update the bit set anymore, as we did with the extended TATS lock, because the bit sets are initialized to ones, and there will be only one writer each time to update the bit set. So in the presence of single writer, intermediate value of the bit set during the write operation represents some supersets of the request resources. That means we always lock enough resources. Okay, here's a very quick code example to show you how to use MRLock on the existing concurrent data structure. Suppose we have a concurrent set which is implemented as a fine-grained locking list, and we want to access key 2758 at the same time. All we need to do is we create a resource request and pass that to MRLock. Once the lock returns, we can operate on the container as normal, knowing that these keys won't be accessed by any other thread until we unlock. So let's take a look at the problem of supporting lock-free transactions. Given a lock-free data structure, we want to support transactions while maintaining the lock-free progress guarantee. So we cannot use locks anymore, or we cannot block any operations anymore. So the illustration here shows you the challenge. Given a lock-free linked list, let's say we want to insert key 4, 1, and 7 in one batch. But at the same time, there might be another thread concurrently deleting node 1 from the data structure before you finish the transaction. So this actually leaves the first transaction in an inconsistent state, which breaks the isolation property. So the challenge for lock-free transaction synchronization is that we need to effectively buffer the write operations so that they are not visible to operations outside the scope of the transaction. And we also need to efficiently roll back failed transactions in order to restore the abstract data structure state. Now, I'm introducing lock-free transactional transformation. This is actually a methodology to transform existing lock-free data structure code into a lock-free transactional data structure. When you apply this methodology, what we can do is we obtain a lock-free transactional data structure that supports lock-free semantic conflict detection. And it will support has a functionality to do logical status interpretation to eliminate rollbacks. And it has cooperative transaction execution to minimize aborts. So all these combined, it provides significantly better performance than the transactional boosting or STM or any existing data structure transaction approaches. So currently, this methodology can be applied to set and map data types and node-based link data structures, such as linked list, binary search trees, Skiplist, and MDList. So in an LFTT, we use node-based conflict detection. For each node in the data structure, we embed a node info structure, which contains the operation ID and a reference to a transaction descriptor. And in that transaction descriptor, it is shared among all nodes participating in the same transaction. So in it, we will store an array of operation types and operands, as well as a transaction status. The transaction status can be either committed, active, or aborted. The concept here is that whenever a thread tries to modify a node, it has to first read the node info structure and hence the transaction descriptor to make sure that the previous transaction is not active. This way, we prevent concurrent modification to the same node, which is equivalent to prevent non-commutative operations from executing on the same key in a set. Now, in the transformed insert function, here is the workflow. The gray blocks are extracted from the base data structure, so we keep those code. We use the base data structure's node traversal algorithm to locate the node containing the key K, and if the node actually does not exist, we will insert it as usual. But if the node does exist, we will introduce a new code path to update the node info structure on that node. If any of these two operations return need to retry, we will restart the whole process again. So in the newly introduced update node info function, what we do is that we first check if the node info has been bitmarked. If so, it means that the node has been logically deleted, and we need to invoke the base data structure's delete function to physically remove the node from the data structure. And then we test if the previous transaction is still active, and if so, we will help finish that transaction. This way, we enforce the serialization at this point so that current transaction will always read the last final result of the previous transaction. After that, we can test if the key is logically present in the set or not. I'll explain this in the next slide, but for an insert function, if the key does not exist, it means that we can actually use cast to update the node infrastructure on this node. Now, here is the truth table for interpreting the logical status of an actual key. So the intuition behind this is that we don't actually need to execute the inverse operation like we did for a transactional boosting technique in order to restore the data structure abstract state. All we need to do is that when a transaction fails, the subsequent operation only needs to inversely interpret the logical status of the key in order to recover the correct abstract state. So for an insert function, if the previous transaction is committed, we think the key is present in the set. An aborted transaction means the key does not exist. And for active transactions, we only consider the key to be present in the set for the operations in the same transaction. So the interpretation for a delete operation is exactly the opposite. And the interpretation for find operation is that we think the key always present because this is a read-only operation will not change the status of the key. Now, once we've done with the transformation of the base data structure code and obtain a lock-free transactional data structure, what we do to execute the operation is that we create a transaction descriptor. And we specify the operations in descriptor, and in that execution function, it will execute the operations one by one. It will continue to the next one only if the previous one has successfully returned. And after all that, it will atomically update the transaction status using the cast to either committed or aborted, depends on if all operations are successful. So there is one additional step, is that we need to bitmark all the node infrastructure on successfully deleted nodes. This way, we can physically remove them afterwards. This is optional, but sometimes this helps performance. The nodes will not interfere with the correctness of the algorithm. It's just improve the performance if we remove the extra nodes from the data structure. Now, there are a few salaries here. Very rarely, a thread may stuck in endless cycling, and this may be because there are cyclic dependencies among transactions themselves. So we detect and recover from this by using a help stack. So before set up to help the other thread, a thread records the current transaction descriptor in the local help stack, and cyclic dependencies are detected as a duplicate entry in the help stack, and then we will abort one of the transactions to break the cycle. Now, if we disable the helping mechanism at all, then it means that we have an obstruction-free transaction execution. The upside of this is that we can now skip the execution context in the transaction descriptor, and we can use many of the existing contention management schemes, such as aggressive, polite, and karma. So here is a graph showing you how LFTT works with a very simple example. 3 threads trying to execute 3 transactions. Thread 1 finished the first transaction by inserting node 3 and 1 into the linked list. And thread 2 inserted node 4, but is currently working on node 2. In the meantime, thread 3 deleted node 3 by updating the node infrastructure on that node. When it tries to access node 4, it actually sees that this node is being accessed by an active transaction. So it has to set out help finish in T2 before resuming deleting node 4. So once thread 3 completes its operation, both T2 and T3 should all be committed, and the key 3 and 4 will be interpreted as absent from the set by subsequent operations. Now, this is code snippet showing you how to actually use the transformed data structure. given 3 sets, instances, and all we need to do is create a transaction descriptor and fill in the descriptor with the desired operations for each set and execute it. Now, we already talk about 2 ways to implement transactional data structures. And some data structures, they can benefit from lock-free or concurrent execution, but some cannot. For example, a stack, because of its inherent sequential semantics, it cannot obtain much performance benefits even if we convert it to lock-free. But concurrent maps is one of those data structures that can benefit a lot from lock-free and transactional execution because of its semantics is inherent parallel. So in sequential scenario, these maps are usually implemented by binary search trees, Skiplist, and hash trees. Now, we definitely want to better performing concurrent map. This will improve the baseline performance because whichever transaction synchronization scheme you choose, this will bring down additional overhead. And all existing implementations, they all have concurrency limitations. So let's take a look at the binary search trees. One problem with that is the binary search trees, the logical ordering of the nodes, of the keys, does not necessarily correspond to the physical layout of the tree. This creates a very problematic scenario for find operation in lock-free execution. So consider a thread tries to find node 7 on the BST, as shown on the bottom. And when it reaches node 9, it gets interrupted. And in the meantime, another thread deletes the node 3 from the tree and changes the layout. So when thread T1 resumes, it does not find node 7. So now it has to decide if node 7 does not exist in the tree or it has to start all over again. This problem, to solve this problem, researchers have been proposing embed logic ordering into the node themselves or use external trees to store all the values at the very bottom so that they have a fixed position. But all those introduce additional overheads. And the more troubling issue is that the sequential bottleneck introduced by the rebalancing process required by a BST. So BST needs to be balanced to maintain their optimal search time. But this process involves modification to a large number of nodes. And this will likely stall other concurrent operations. To the best of my knowledge, there is no lock-free implementation of rebalancing algorithm for BST. But people have been proposing relaxed balancing and background balancing to alleviate this issue. So a better candidate for building concurrent maps is using the Skiplist, which is a probabilistically balanced alternative to BST. In a Skiplist, it contains nodes with multiple links. And at the very bottom, the nodes form a linked list, and the upper level links are created with exponentially lower probability so that they guarantee logarithm search time. And also the upper level links, they are actually redundant shortcut links into distant nodes. So one problem with Skiplist is that the insert and the delete operation, they will modify multiple nodes. What do I mean by this is that consider we are inserting node 4 and 6 in the Skiplist. Inserting node 4 requires us to modify links on node 1 and 3. Inserting node 6 will require us to modify links on node 1, 3, and 5. If this is a simple linked list, these two insertions should have no dependency or interference. But in the Skiplist, they all need to modify node 1 and 3. Only one of them will succeed and the other will retry. So Skiplist introduced additional access conflicts among supposedly commutable operations. Now, what makes an efficient log-free map based on these observations? We want to maximize the disjoint access parallelism. And the data structure preferably should have low branching factor so that we can avoid hotspots, and it should have localized updates to avoid access conflicts, and fixed key position to simplify the process query. Now, in the proposed multidimensional list, the lower level nodes will have smaller branching factor, which brings down the average branching factor of the data structure. And insert delete function only modifies 2 adjacent nodes at most. It has a fixed layout for a fixed set of keys and does not require balancing or randomization. Now, the intuition behind MDList is simple. Here is the linked list, and the insert and deletion function on the linked list is very efficient, requiring only 1 cast update on the pointer. But the search is linear, and which is not ideal for large key space. Now, what we can do is we can rearrange the linked list into shorter sublists and do search within each sublist. In this case, for this example, we have 16 nodes, so we arrange the linked list into 4 columns. What if we could first determine which column a key belongs to and do a linear search within that column? That would be much faster. Now, based on this observation, we came up with the 2D list. We replaced the links from the bottom nodes to top nodes with links among the top nodes. And we introduce a 2-dimensional vector which serves as a coordinate for each node. The nodes are arranged by the lexicographic ordering of the coordinates. And in this case, the worst case search time becomes the square root of n. If we could further generalize this into higher dimension, we could further reduce the search time. Now, here's just the definition of the multidimensional linked list for your reference afterwards. I'm going to skip into the example of a 3D list, which will make things easier. Now, in this example 3D list, we have 3 dimensions, D0, D1, and D2. Along each dimension, the nodes form a sublist. So for dimension 0, we have 1 sublist. And for dimension 1, we have 4 sublists, which are those vertical columns. And for dimension D2, we have several sublists, which are those sublists pointing backwards into the slides. So in order to support lexicographic ordering of the keys, we need to first map the scalar keys into a high-dimensional vector. This mapping function should be injective and monotonic so that we can preserve the ordering of the keys. Now, the map function should also be, preferably should be uniform so that we reduce the average search time of the whole data structure. In our case, we can simply use numeric-based conversion to achieve this goal. So let's choose a base based on the key universe size, which is the total number of keys, the dth root of the key universe size as the new base. And then we convert the decimal number to the new base. We treat each digit as the coordinates for the MDList. So here we have a key universe of 64 keys, and the dimensionality of data structure is 3. So the new base is 4. When we convert the key 63 in decimal to 334 in base 4, we obtain the actual coordinates for that key. The find operation on MDList will recursively traverse 1 sublist on each dimension until it reaches the target node. So the green arrows, they highlight a path from the root node to the node 332. When traversing each sublist, it only compares 1 coordinate at a time. So when the search function traversing the D0 nodes, they only compare the first coordinates of the nodes with target nodes. And when it's traversing the D1 nodes, they only compare the second coordinates. Now, the worst case search time in this case is bounded by the total number of dimensions multiplied by the maximum number of keys on each dimension. If we choose the dimensionality of this data structure to be a logarithm of the key space U, then we can obtain logarithm search time for the worst case. Now, the insert function consists of 2 steps. The first step of node splicing actually connects the new node to predecessor nodes. This is very similar to what you do with a lock-free linked list, and this can be done with a cast pointer update. So the predecessor query will return the predecessor node and the current child of the predecessor node, and the dimension of the new node and the new dimension of the current child. Now, In this case, we are inserting node 200 after node 102. The original child of 102, which is 201, will be pushed back down to dimension 2. In this case, the child nodes marked by the red arrows will no longer be accessible from node 201 because the slot has been given to 200. So we have to do an additional step to transfer these two child nodes back to the new nodes. So the child adoption process is only necessary if the dimensionality of the current child is changed during the insertion process, which means that if the DC does not equal to DP. So we should transfer all the child in this range to the new node. And since this is a process requiring modification to multiple pointers on the current child node, we use the descriptor to encapsulate the context and allow other threads to help finish this process if this process gets delayed. Now, normally, we could delete a node from the data structure by doing the inverse work of an insert function. But this wouldn't work for a log-free version because the insert function may promote or demote a node, which is to increase its dimensionality. And the delete function may promote a node, that is to decrease its dimensionality. So due to the helping mechanism, several threads may access the child adoption on the same node without additional synchronization. We cannot know if all of them have finished. So data races may arise among ongoing child adoption tasks and the child transfer process. The solution is to keep dimension change unidirectional. So we introduce a symmetrical delete, which is a logical deletion process that decoupled from the physical removal of the node. So here, we want to delete node 102. We first bitmark the node to indicate that's been logically deleted, but the node is still in the data structure and is valid for routing. Now, we only purge the node from the data structure when a new node is inserted immediately in front of this node. This way, we can transfer all existing child nodes of the deleted nodes to the newly inserted nodes using the same child adoption process. This simplifies the help protocol and simplifies the synchronization. So since we are using logical deletion, the abstract state of the map becomes two parts. We have a set of all nodes and a set of logically deleted nodes. The abstract state of the map becomes the set M minus set P. So the linearization point for insert function is when the cast updates predecessor child pointer, and the linearization point for delete function is when cast marks the predecessor child pointer, and the linearization point for the find operation is when the child pointer is read. Now we did our experiments on a 64-core NUMA system with 4 AMD CPUs, and we compile our source code and benchmark using GCC 4.7 with level 3 optimization. So for the experiment test, MRLock, we randomly, for the MRLock and its alternatives, we randomly acquire up to 64 to 1,024 resources. And for the data structure obtained by LFTT and MDList, we test them under write-dominated, read-dominated, and mixed workloads. So here are the alternatives we chose for the MRLock. For two-phase locking, we use STD lock and together with STD mutex and boost lock with the boost mutex. And for resource hierarchy, we use it with the STD mutex as well as the Intel's TBBQ mutex. Now, these two graphs here shows the execution time for acquiring a million locks, acquiring and releasing a million locks on 16 threads. On the left, we have the execution time for 64 resources. What we can see is that the x-axis represents the resource contention level, which is the number of requested resource divided by the number of total resources. As we increase the number at the resource contention level, the locking protocols, including two-phase locking and resource hierarchy, the execution time all increases linearly. But for MRLock and the extended TATS lock, the execution time kept almost constant. This is the a major difference between batch locking and the locking protocols is that the batch locking is insensitive to resource contention, because how many resources you are requesting is only handled in the same way. Overall, the MRLock outperforms the best performing alternative, which is the resource hierarchy with a Q-lock by up to 3 times for 64 resources and up to 5 times for 1,024 resources. One thing to note is that when the resource level, contention level is very low, actually the locking protocols, they have a huge advantage because the batch locking, they have a fixed startup overhead. And here we show how the execution time scales with the increasing number of threads. Now, as we increase the number of threads, the graph on the left shows for resource contention of 50% on 64 resources. The extended TATS lock actually performs really well with a small number of threads, but as the number of threads increases, the contention level arises at a single memory location, and eventually on 32 threads, the MRLock begins to outperform the extended TATS lock. Now, for the 1,024 resources, the MRLock outperforms the alternatives all the time. Now, the next benchmark is to test the transactional data structures. We test 2 transactional data structures, one transactional Skiplist and one transactional linked list. For Skiplist, we compare 3 versions, the log-free transaction transformation and the transaction boosting, as well as the object-based STM. And for linked list, we compare with the transaction boosting and the word-based STM. Now, in this graph, we show the throughput of the data structures for mixed workload on the NUMA system with 1 million key. Now, the higher throughput, the better. So, and also we append a number to the name the name of the data structure to indicate the transaction site. So LFTT means log-free transaction transformation with 2 operations per transaction. Now, overall, the LFTT approach obtained an average of 60% speedup over the boosting approach and 3 times speedup over the STM. And we can see that as we increase the size of the transaction, the overall throughput of all approaches drops slightly. And this is because when we increase the size of the transaction, if one operation fails with a larger transaction, it forfeits actually a larger amount of work. So this will cause the drop in throughput when we increase the size of the transaction. And now, the bottom half of the graph actually shows the number of spurious boards for each of the approach. The spurious boards means that the number of boards, number of total boards, not counting those caused by failed operations. This is actually a measurement of the efficiency of the contention management scheme. Now, since we're using helping, so for Skiplist, most of the time if we encounter a conflict, the thread will set up to help each other, hence there will be no aborts. But for ASTM and the boosting approach, the number of boards is pretty high. So here we show the throughput for linked list with mixed workload with 10,000 keys. So for startup with the small transactions, we only obtain a very small advantage over the boosting approach. But as we increase the size of the transaction, we're getting more performance benefits over the boosting, because in the case of larger transaction for the linked list, it is actually very expensive to execute the reverse operation on the linked list than in a skip list. So the performance of the boosting approach will drop significantly after we increase the size of the transaction, where we encounter more aborts and retries. Now, for the number of spurious boards, we do encounter a small number of spurious boards in this case for larger number of threads, but it's still 2 to 3 orders of magnitude less than the alternative approaches. So for the MDList-based dictionary, we compared against the log-based and log-free and RCU-based BST. We also compared with the 3 log-free Skiplist implementations. Now, this graph here shows the throughput of the all the maps with 1 billion keys and 50% insert, 50% delete operations. So this is pretty write-heavy workload. We can see that we obtain as much as 100% speed up for 60 resources. Because the MDList, it has really optimized for write operation with only, it only modifies on most 2 nodes. So for this kind of workload, it's just performs the best. And if we decrease the key size to 1 million and increase the read operation with a mixed workload, we can see the MDList can still obtain up to 50% speed up over the best performing Skiplist. Now, when we come to a case where we have a really small key range, let's say 1,000 key and a read-dominated workload with 90% find operation, this is when the BST really begins to shine. Because BST have really shallow depths in the scenario, and for 1,000 key, the dimension we choose for the MDList, which is 16, is too large. It has too many overhead. So here, this graph shows actually parameter sweep on the dimensionality of the data structure as well as the number of threads. So the thing to note is that this is for write-dominated workloads with 50% insert and 50% delete. We can see that the maximum throughput of the MDList always converges through the 20 dimensions. This means that the throughput of this data structure, it is independent from the concurrency level, but dependent on actual work level. So what we can do is that we can train this data structure according to your specific workload, and then when you add in more threads, it will scale automatically. So to summarize the performance characteristics, the MRLock excels at medium to high levels of resource contention and is suitable for a large pool of resources. And the LFTT-based transactional data structure excels at the larger transactions, and it has improved the success rate with minimal spurious support. And the MDList excels at a high level of concurrency and large key space. It is optimized for write operations. Now here is an overview of the Libtxd. At the very bottom level, we have 3 unmanaged containers, which are log-free data structures without memory management scheme. These data structures will be used internally or externally by the memory management module and the log-free profiler logger. Unmanaged means that their memory will not be reclaimed until the data structure itself is destroyed. So on the upper level, we have 2 strategies. The MRLock, we provide a resource mapper that allows you to map abstract logs into the bit set in MRLock to be used with conventional log-based data structures. And the LFTT we provide for data structure building list, MDList, Skiplist, and the hash table with 2 type of interfaces, set and map. Now, in the future, we plan to support wait-free data structures. The work to be done is to add wait-free, add a procedure to support wait-free update on the node infrastructure and to have wait-free memory management system. We plan to also support the non-linked data structures, but this way we have to associate the node infrastructure actually with each data item. And we maybe also we can do automatic code transformation to actually obtain from an existing log-free data structure just to apply a transformation, allow user to identify the code blocks, and we will give the transactional data structure as an end result. Now here's some references to the contents and the link to the source code as well as our contact emails. That concludes my talk, and I'll take any questions you have. All right, questions? Yeah. So the question was, are we proposing anything for the C++ standard? Is that right? Not right now. No, we are not proposing anything. We're just building this as an experimental external library for user to use for experiments with concurrency. All right, thank you.